This meeting is being recorded.
In section 13.5, we're introduced to how ethers are prepared. So we're given this example here of the industrial preparation of diethyl ether. And this is accomplished using an acid-catalyzed dehydration of ethanol. So that's what we're shown here. So we see that our acid catalyst is utilized and ethanol is protonated. And then through an SN2, a nucleophilic attack, we see this addition of another ethanol to our complex here. And then in a last step here, in a proton transfer, that extra proton is removed and we can end up with this diethyl ether. So you should note that simple symmetrical ethers can be prepared in this fashion, but we may need alternative mechanisms for a more complicated synthesis. So for example, the Williamson ether synthesis can be used to create some asymmetrical ethers. So we see here that we have an alcohol starting material. And in our first step, we can use a strong base such as sodium hydride here to deprotonate our alcohol. And our resultant alkoxide ion then would become a nucleophile and attack our alkyl halide here in a nucleophilic attack. So this would cause that loss of leaving group, whatever that halogen is to leave, and then we would end up with our ether product, and we can see that it's been color coded so we can keep track of where the R group from our alcohol came from and then the R group from our alkyl halide came from. And of course, we'll end up with whatever that sodium salt is as well. So the mechanism, again, begins with this proton transfer in our step one, where a proton is abstracted. We deprotonate our alcohol. We end up with that alkoxide ion. But we should note that since this is an SN2 substitution reaction, it would only work well with an unhindered, so a non-sterically hindered primary or methyl alkyl halides. Secondary or tertiary tend not to be involved in this type of synthesis or not work properly. So we have those two possible routes to synthesize methyl tert-butyl ether here. So these are our two scenarios. So in this top scenario, we have our tertiary alcohol used and a primary, or rather a methyl, right? CH3I here. So this is a methyl halide. And we can see that we would be able to use this route because it uses that methyl halide. So we can incorporate that into this Williamson ether synthesis. Now, if we tried the alternative, if we tried to use a methyl alcohol here, a methanol, and then use a tertiary alkyl halide, this would not progress because, again, we do not have an SN2 mechanism possible with a tertiary substrate. So this route, we say, does not work. So that's how we have to choose between, do we need a tertiary or secondary alcohol versus a primary or a methyl alkyl halide. So there's one last route that we can discuss when we talk about the preparation of ethers. So we know that oxymercuration, demercuration, as we saw in section 8.7, can be used to create alcohols. But if we change this to alkoxymercuration, demercuration, we can see a similar mechanism, right? This new approach here, this alkoxymercuration, instead of an OH being added over here, we add an OR. So again, we have an alkene starting material, we have our mercuric acetate, and now an alcohol instead of water being utilized. And then, of course, our sodium borohydride in step two. So we can create ethers through this last mechanism, this alkoxymercuration, demercuration, as well as the Williamson ether synthesis and the others that we looked at.